Okay, so we're going to talk about the next kind of special right triangle, which is a 30, 60, 90 triangle, which comes from an equilateral triangle. And so I draw this equilateral triangle. And so the way to really think about it is just to kind of understand that I need to deal with a special right triangle. So I'm just going to put a right triangle off to the side here, and we're going to come to it. And so we're going to kind of derive how we get all the rules that come out of the special right triangle. But this is something you should be doing with me if you really want to understand it. You should build this as I do it. It'll help you. So how do I look at this in relation to this? Now, obviously, they don't look alike, but this right here is going to be related to this, and we'll get there. So first, let's just talk about this. Since it's an equilateral triangle, and that's what we're trying to deal with, I know that all the angles here are 60 degrees. Okay. Now, one thing in geometry you have to take into consideration is you go by what the information in the diagram says, not the appearance of the diagram. So the information tells me it's equilateral, even if it doesn't appear to be. So I can use that information in that way because drawings can be misleading. So the information is what we have to use to determine that information. So we look at the diagram, and then we look at the information, and we use it to say, okay, well, if I drew an altitude down the center of this, right, it would be like breaking it into two equal triangles. And then I could take, let's say this is A, this is B, and this is C, and we'll call this point D right here. I know that's a right angle. So this would be point D right here, and this would be A, and this would be B. And so all I've done is pull out this triangle over here, and this is 60 degrees. And now notice that if this is 60 and this is 90, this is 30. And so that's where we can kind of see that we're talking about 30, 60, 90 triangle. It's just one half of an equilateral triangle. So we're going to kind of build it. And so I'm going to use S to represent the sides. So all three sides of this equilateral triangle are S, but I'm going to double it. So I'm going to make them all 2S. And the reason why I'm making it 2S is so that later on, as we kind of look through this, algebraically speaking, or from an arithmetic perspective, it's a little bit easier to deal with integers than fractions. So this will make it easier to visualize that as a general rule. So we can take this information, we can expand it, since we know ABD. AB is 2S. And what about AD? Well, AD is half of 2S, so it's 1S. Of course, the 1, I'm just putting it there. And so, as for show, so because there would be no number there, but it just helps us understand the relationship. And I'm going to write down that this is the hypotenuse, and then that this right here is the short leg, and this leg over here is the long leg. And it's important that we kind of think about them separately, right? The short leg should be opposite the shorter angle, right? And if this angle's degree is 30, and this is 60, this side should be longer than this. So if this is 1s, this has to be greater than 1s, but less than the hypotenuse, which is 2s. So we can use Pythagorean's theorem, just like we did for the 45, 45, 90, to kind of evaluate this relationship. So I want to find this long leg here. We'll call it L, right? So I can say that a squared plus b squared equals c squared. Therefore, I know that c squared minus b squared would give me a squared, or c squared minus a squared would give me b squared. So if I work backwards from the hypotenuse, I can find a leg. So I can take the hypotenuse, and I put it in parentheses, and I plug it in for c, because it's the hypotenuse, and I subtract a or b, right, which is 1s squared. That will give me the leg. And I like using cursive L just because it makes it easier rather than writing it uppercase. But your choice is. I guess I'll make this a cursive L just to stay consistent. And so, sorry, just sharpening my pencil. And so I can distribute this to both of these. So I get 4s squared minus 1s squared, and that will equal the leg squared. And then I can add these two together. I get 3 side squared equals the leg squared. So again, we just work backwards using Pythagorean's theorem, and I'm going to break these up, the perfect square to the front, and it equals the leg squared. And we already know taking the square root of this perfect square just leaves us one of those values. So the long leg, which is L, is equal to the short leg times the square root of 3. Ooh, I just lost my pencil tip. Good news is I have other pencils. I'll just have to go to one of those. It's not a big deal. So we see that the leg is the short leg, the long leg is the short leg times the square root of 3. So we go up here and we kind of look at that and we can say, all right, well, how does that help us? So if I can just create a triangle real quick, and I'll do that just for this sake, and I apologize that this wasn't created ahead of time. I'm just going to kind of do this kind of makeshift real quick, but I have this right triangle, and I'm going to say this is 60 and this is 30 just because the organization of it, but we were talking about the short leg and the long leg. So if I tell you the short leg right here is 4, well, then what is the long leg? The long leg, just plug 4 in here. It's 4 square roots of 3. And what is the hypotenuse? Well, this right here, so this is telling us that the long leg equals the short leg times the square root of 3, right? That's just algebraically what's happening. So the short leg times the square root of 3. I know that this is the long leg. Now, the hypotenuse right here is really actually just 2 times the short leg because it's 2 s's and the short leg is 1 s. So the hypotenuse, right, is equal to 2s. Well, if I know that the short leg is 4, then the hypotenuse is equal to 2 times 4, which is 8. And so the effect is that you can use Pythagoras' theorem to kind of find different parts of the shape if I give you one segment given 30, 60, 90. Now, if I was thinking about it, right, and I told you that this side was 4, you might have been able to rationalize that this side was 8 without doing any calculations, right? Because we know that the organization of this triangle, and I apologize, it doesn't look right, but that this is 60, which means that if I kind of went back, that this 8, this side would be 8, and this whole side would be 8. So if this is 4, this would have been 4. So it's how you can kind of go back and prove that this side is 2 times the short side. And then, of course, this side is just the long side times the square root of 3. So I'll put a couple of examples up, and then we can look at those together, and then you can try them. Thank you.